Oh,
All right. Our next speaker is Cory Dean from Columbia University. His title is Correlated States in Transition Metal Dichalcogenides. Please go ahead.
sorry, I'm trying to get out, trying to gain control here. Okay, here we go. Good. Okay, thank you for inviting me to this conference. For those who've been attending all day, thanks for sticking around. I guess this is recorded, so you might be seeing this later. What I'm going to do is shift gears a little bit. Jevin, just let me know if I'm about to go long, because I won't necessarily be watching the clock. So just let me know when the time is up. Yeah.
Sure.
Okay, thanks. Yeah. So I'm going to shift gears here a little bit, not dramatically. What I'll continue to be talking about is basically Moiré pattern systems and correlated states that derive from imposing some kind of Moiré pattern. But we're going to move away from graphene and talk for the majority of my talk about the transitional dichalcogenides. So my talk will take two parts, essentially. And if there's time, I'll add a third. Basically, what I'm going to do is first discuss the kind of ideas of there being correlated states and Moiré-induced flat bands in the TMDs. This is going to be a review of work that we published about a year ago or so. And then next, I'll talk about some more detailed studies we've made of these states, in particular, the transition of the insulating state and some other measurements we made of the insulators in these systems. And then at the end, both of those sort of sections, we'll talk about homobilayers. So WSE2 is what I'll be discussing primarily. And then at the end of my talk, with as much time as I have remaining, I will add some discussion about heterobilayer work that we've done recently. And mostly I'll be kind of summarizing some open questions we have about these systems. Okay, so first, so we saw this morning a nice summary of twisted bilayer graphene. Remarkably, so as we were reminded, this was first reported only like 3 years ago, and yet there's been an immense amount of work and development of understanding and continued excitement and progress in this field. Very simply, what we understand now is that we can gain, this is basically a universal quantum system. We can gain access to almost any correlated, state that you might want to study in the twisted bilayer graphene. And more generally, what I just want to highlight for this talk is that, as was already discussed, these systems are already quite well understood. There's a lot of reproducibility despite the intrinsic sort of disorder and challenges that we have towards realizing uniform devices. In spite of that, there's sort of a broad understanding of how these systems behave as a function of twist angle, as a function of doping. And even now when we couple twisted bilayers to other lattices like BN, et cetera. Okay, so summary statement here is just that we know what twisted bilayer graphene is. I'm not going to review that in detail. And we fairly well understand it. There's some exciting open questions remaining, but generally we have a good picture of it. So the question I want to ask is, what about the other systems? So soon after twisted bilayer graphene was reported, people kind of immediately started thinking about, can similar physics be accessible in other twisted bilayer systems? And we know that there's a whole host of exfoliatable materials, among which we can access really a wide range of single particle and also many body states within these systems. So the question generally is, if we put any two layers on top of each other and twist them, we generically will get a Moiré pattern. What does that Moiré pattern do? Can we induce flat bands? And what kind of states arise out of those flat bands? Again, I'm going to focus on the transition metal dichalcogenides specifically. These are semiconductors consisting of a transition metal bound to two chalcogens. And in particular, for the next while, I'm going to talk about WSE2. And the reason we tend to study WSE2 is two just very technical reasons. One is that we have a local collaborator who can grow very high quality tungsten diselenide, so that makes it convenient from a materials point of view. The other is that we've made good progress in learning how to make good electrical contact to this material. So that's, for those experimentalists or those just interested, one of the main limitations, in my view, experimentally of these systems generally is, how do we probe their transport properties? And there's a real sort of technical problem getting just good ohmic contact to survive at low temperature. So I'm not going to delve into that too much or really at all in this talk, just to highlight that we've developed some recipes that seem to be reliable for WSE2. And if people are interested, I'm happy to discuss after or sort of offline. Okay, so this though is a good representative, system for any of the TMDs. They all have basically the same kind of structure and some version of the same band structure, more or less. The idea here is that, as viewed from the top in the bottom left cartoon, we again have something that looks like a honeycomb lattice. But it's not a honeycomb lattice in the same way that graphene is, in the sense that there is a difference in the A and B sublattice sites in this system. And this gives rise to a band structure that has a band degeneracy, but not really. One of the interesting things about this band structure is that there ends up being a locking of valley and spin ordering in the system. And within each valley, there ends up being a splitting of the spin ordering due to like spin overcoupling. So altogether, that gives rise, sorry, I got to change this. Give me a second. That gives rise to a scenario where we have K up, and K prime, K down as the two degenerate energy bands. And those are energy separated from the lower spin K and the upper spin K prime bands, et cetera. So all that means maybe for this discussion for now is that the band structure here is slightly simpler than it is in graphene, in the sense that we've reduced, or I guess it's the same at this point. We have an increased number of degeneracies. We've coupled two of the degeneracies. So we have K coupled to spin up and K prime coupled to spin down. Okay, sorry. Good. So now if you place one of these materials on top of another, just like the scenario when you have graphene or graphene coupled to any other honeycomb structure, what you expect is that if the twist angle between these two layers is non-zero, a Moiré pattern will develop. And immediately following sort of the kind of, publication of the twisted bilayer graphene results almost immediately, several theoretical papers, I'm just highlighting a few here, pointed out that indeed you expect that you will get generically a flat band to emerge in any of the sort of homobilayer systems, WSC2, WSC2, MOS2, MOS2, et cetera. And this also extends to heterobilayers, which I'll talk about sort of near the end of the discussion today. Okay, so I'm just saying here, there's really flat bands everywhere. As Pablo pointed out this morning, really this kind of Moiré superlattice-induced flat bands becomes a generic property of kind of any system in which we have the ability to sort of induce a Moiré superlattice potential, really. Okay, but now there's a critical sort of important sort of feature here that distinguishes the origin or the sort of character of the flat band that exists in these systems that makes it quite different from graphene. And that's sort of, if you think about exactly how the flat band arises. So in twisted bilayer graphene, the picture that we have is that in K space, if I have the two layers are rotated in real space, in K space, that results in a shifting of the Dirac cones, separated in K-space, sorry. And what happens is in this system, these two layers will basically hybridize at the point where these displaced cones cross. And that gives rise to basically a gap in the spectrum here. Sorry. Okay, so you get this hybridization gap. And what that does is it results in basically the formation of this low energy band. And the overall width of this low energy band in this cartoon picture is just fairly simply a function of how physically separated these bands are in K-space. So that relates to the twist angle and how big this hybridization gap is. So basically the size of the hybridization gap matches the energy scale that corresponds to the point of crossing these bands to the charge neutrality point. If those two are equal, then you get the flattest band possible. And that gives rise to this magic angle at which there is this very sort of flat band defined at a very precise angle. For the case of twisted WSC2 or any of the TMDs or any semiconductor, really, the situation is quite different. If I had a semiconductor, in this case, I'm going to look at a homo bilayer, I can imagine that I have a similar scenarios with the twisted bilayer graphene. I've got these two bands that are displaced in K space. Now I'm drawing here basically the K prime up and the K down values. I'm ignoring any higher energy or low energy bands. There again is the sort of opportunity for these bands to hybridize. That hybridization gap basically cuts off, in a sense, in this case, the top of the valence band or the bottom of the conduction band. And again, I end up with a low energy band, an isolated low energy band in the system. In this case, however, again, the position at which this hybridization gap emerges is a function of angle, and the size of the gap is a function of, it's related to the degree in which the bands hybridize. But now I've got sort of a hard stop in this band. So there's sort of, I'm sort of bounded by the intrinsic band edge. So what that means in some kind of schematic way is that while for twisted bilayer graphene, there's a precisely defined magic angle at which you have the minimally flat band, in twisted homobilayer TMDs, you imagine that basically the width of this band grows continuously as you twist the two layers. Now, the relevant sort of feature here is not just how flat the band is, that's an important parameter, but it's actually that related to what the Coulomb energy is in the system. So we're interested in stabilizing correlated driven states or interaction energy driven states. And the way one sort of hopes to do that is not just that the band is minimally flat, but the band width is less than the Coulomb energy. So really it's that ratio between the two that's defined at a well-defined magic angle in twisted bilayer graphene. And in twisted homobilayers, what I'm trying to argue is that actually there's a continuum of twist angle that's not a precisely defined angle over which you might expect that the Coulomb energy exceeds the bandwidth. So we kind of tongue-in-cheek, identify this as the possibility of realizing a magic continuum in the homobilayer TMDs, or indeed if you had a superlattice potential applied to any semiconductor and the wavelength were appropriate, you might imagine that you could access this kind of situation where you get a strongly correlated flat band. Okay. So that's kind of the cartoon idea. What happens in real systems? So a little more than a year ago now, we realized this scenario, again, using twisted WSE2 for the reasons that I discussed a moment ago. And we fabricated a device that's at some twist angle, and we measure the transport response. And what do we see? So in this device, what we see is that, so first of all, we're operating in the, always in the valence band of this material. So I'm always operating at the top of the valence band, which I'm showing schematically here. And what we see is that, first of all, as we sort of try to inject carriers in the system on the right-hand side of this plot, because this is the valence band, we're going to label the densities as negative values. On the right-hand side of this plot, we're just in the intrinsic gap of WSE2. And as we dope or increase the hole density to the left, the first thing we see in this blue curve, this is a device with twist angle 4.2 degrees, is we see a resistance peak in the response at some point, and then we see a second resistance peak in the response. Now, one of the challenges of these materials, again, is that it's difficult to make good contacts to them. And so can be somewhat of a challenge generally to understand, what your density values is. It's hard to pinpoint where the actual band edge is. Hall effect measurements are problematic because we're trying to measure Hall responses with, very poor contacts in general. But as I said, we sort of made progress, and in these devices, we were able to kind of address those issues. So we could identify not only that we have these peaks, but what filling do those correspond to in the picture where what we've done is really created a low energy band in our system. Okay, so the way we do that is, sorry, I sort of jumped the gun a little bit here. The way we do that is from Hall measurements, and really in these devices, we were able to identify essentially Shinnecock-Dawes oscillations near formation of quantum Hall states at high enough field. And we can identify these kind of Landau fans, and we can project those Landau fans back to precise density points at zero field. And that allows us to identify really in a fairly precise way band fillings. So in this figure, projecting to zero field allows us to identify on the right where the intrinsic top of the valence band is, the intrinsic band edge of the WSE2 is. And then on the other side, we see these fans allowing us to project to where full filling is. That allows us to identify in density units that this peak is actually a full filling peak. And here, where we can identify where the zero filling band edge is. So we can make the conversion, therefore, from density to filling. We can identify that this peak here really is at half filling. So I'll get to a moment maybe why the half filling peak is larger than the full filling peak, for those who have that question. So here when I say half and full filling, a little bit the nomenclature wandered over time. I want to be sort of clear about this. So in our system, we have a twofold degeneracy. So full filling corresponds to exactly 2 holes per Moiré unit cell. And here, if I refer to half filling, what I mean is 1 hole per Moiré unit cell. That's the condition I'm in. And here in the top right, all I'm really sort of identifying is that indeed, if we look at the temperature dependence at this half filling position, then that looks very much like an insulating state. It's not just that we have a resistive peak at low temperature. It really has in insulating and like temperature dependence. And as I dope slightly away from there, I transition from an insulating like temperature dependence to a metallic like temperature dependence on both sides. Okay. So in this system, as I emphasized at the beginning, we have this broad range of angles over which we might induce some kind of low energy band, and where we might imagine that the bandwidth is less than the Coulomb energy, so we might maintain the opportunity for seeing correlated driven phases. And indeed, we find that that's the case. So here we have a range of twist angles. These are all measured on different devices now, spanning 4 degrees to 5.1 degrees. And what we see is that in each of these devices, by transport, we're able to identify a feature that looks like a resistive feature at exactly half band filling. And as we increase the twist angle, that corresponds to a decreasing of the Moiré wavelength. And as one expects, the half band filling point for smaller wavelength requires more density of holes to reach 1 hole per unit Moiré cell. That shifts to higher and higher density, just as expected. Okay, so that tells us really 2 things. One is that the twist angle results in an evolution of the band width in the way that we expect. The other is that there is a finite range of angles, in this case, more than a degree of twist angle, over which we see the emergence of a feature at half filling of this band. And to be precise, I forgot to mention this, single particle band structure would not necessarily indicate that there should be any feature at half filling. Really generally at all. And so we take this as evidence that we have basically a correlated driven insulating state that's emerging and half filling this flat band system. Okay, so we can study that a little bit more. One of the things we did early on was to look at displacement field dependence. So in this image on the left here, I don't show it, but we can have a gate on the bottom of this device and a gate on the top of this device. And in combination, those 2 gates allow us to independently tune the band filling and transverse displacement field. So we can sit at fixed filling and vary the transverse displacement field. And what we find when we do that is that this half band insulator actually exists only over a fairly narrow range of displacement field. So that's plotted here. I'm plotting resistivity, and basically red indicates a resistivity peak and blue indicates low resistance or relatively low resistance. And what we see is that this half band insulator really sort of seems to stretch along the half filling point. So fixed half filling is along this dashed line here. But over a finite range of displacement field, it sort of appears and then it disappears again. Okay, so here I'm showing just some line cuts demonstrating that as a function of density, indeed, I see like a resistive peak at different displacement field values. And here I'm just showing that we can sort of extract the energy gap associated with this peak. It really, again, shows an insulating-like behavior. So just through activation measurements, we can extract a gap value. And not only does the resistive peak follow this kind of shape that I'm showing in this color plot here, but the gap evolves in a way that you might expect also. Okay, so one question is immediately, can we understand what it is we are looking at here? So one of the ways we do that is we look at the magneto transport around this half band filling point. That's what I'm plotting here on the right. So the top is plotting longitudinal magneto resistance, and the bottom is plotting the Hall resistance. In the middle column here, what I'm doing is taking a point in this 2D plot that's in a situation where we have a well-defined gap at half filling. And then on the right, I'm measuring a similar response, but where we've moved off of the resistance peak. So we're still at half filling in these 2 plots on the right, but at a displacement field value where there's no longer is clearly a resistive state. So what we see in these 2 plots is the following. And if we focus on the Hall resistance, what we see in the middle column is that when we have a well-defined insulating state at half filling, we identify that actually the Hall resistance inflects 3 times at that point as we sort of dope around that half filling point. And in the case where we have no insulating feature at half filling, the Hall resistance doesn't really show necessarily any feature at that point. We do see an inflection in the Hall resistance at some value, but that occurs at a different value that's not does not coincide with half filling per se. Okay, so how do we understand this behavior, and what's this telling us about what we understand in the system? So just a very quick cartoon summary of what Hall resistance is really telling us, we think, in this scenario. If I just had a single particle band that I could completely fill. So that's what I'm drawing here. Then what I necessarily expect is that at some point in that band, I'm going to encounter the Van Hoff singularity, which in this case just defines where the curvature will change, transition from, I'm drawing a valence band here, from hole-like to electron-like. Okay, so at some point in this band structure, necessarily that Van Hoff will exist. And if I measure Hall effect, as I dope through that Van Hoff singularity, I expect the sign of the Hall to change. It will change from having a hole-like sign to the electron-like sign. In a scenario where I take this single particle band and I envision that I introduce some subband gap for some reason, perhaps we have an interaction-driven insulating state, for example, then necessarily what you might expect is that now I have to change, I have to inflect the sign of the carrier through the band more than once. And indeed, you can identify that you would expect it to happen really 3 times. So I now have something like a Van Hoff singularity emerging right before the gap sort of, appears. I would transition in sign around the gap, and then I would see another transition at some kind of, higher doping. And the only kind of thing I'm trying to identify here is that really, if there's no subband gap, I expect there to be a single Van Hove-like characteristic signature in the Hall resistance. And if I open a subgap, I expect there to be 2 more inflection points in the Hall, in the sign of the Hall resistance. Okay, so let's go back to our data. Now I'm looking at sort of line cuts of the Hall resistance here. And indeed, what we see is that as a function of displacement field, we observe a transition that looks exactly like this cartoon picture that I painted. So at some low displacement field, we see a single crossing, a single sort of variation of the Hall sign as we move through the entire band. And then at some point, we see now the emergence of 2 additional crossings in the Hall sign. Now, the other thing I want to really kind of point out here is that between panels 2 and 3, for example, the relative positions of what we call N1 and N2 are not changing that much, but the relative position of what we call N Van Hoff singularity is really changing more dramatically. And we interpret this response as indicating that this Van Hoff position is something like the intrinsic Van Hoff position in the band, whether there exists sort of the spontaneously opening gap or not. That's sort of our interpretation of this value. So we're going to track this value N Van Hoff singularity and assume that that basically would track with how we might imagine that the Van Hoff position evolves as a function of applied displacement field in a single particle picture. That's our interpretation. Okay, so what do we see? So what we see is that this quantity we call the Van Hoff singularity, its position as a function displacement field begins slightly below half filling, and then as we increase the displacement field, it moves through half filling and then moves far away, moves to a much higher density. And what we also notice, that's plotted in black here, if we plot in red the magnitude of the half band resistive feature, that resistive feature is relatively weak at 0 displacement field. It grows and becomes strong, and becomes strong evidently coincident with the Van Hoff singularity crossing the half band point, and then it becomes weak again. Excuse me. Okay, so this tells us in our data, we think this tells us that basically we have a resistive feature that always is appearing at half band filling, but its strength depends on whether the Van Hoff singularity is at half filling or not at a half filling. So it tells us also simultaneously necessarily that the insulating state that we've identified, a half band insulating state, does not follow the Van Hoff singularity. So it does not occur where the Van Hoff singularity occurs. It occurs at half filling always, but its strength is dependent on whether the whether the Van Hoff singularity is coincident with half filling or not. Okay, so we can put all this together, I think, in a sort of nice correspondence with a nice theoretical picture. So this is band structure calculations done by our collaborators. And in particular, what we worked with them to do was to try to figure out what does the band structure of this homobilar WSC2 look like, and how does it respond to applied displacement fields. And what I'm showing here basically is band structure calculation that reflects on the right cartoon picture. Here's the solid blue is basically the top of the valence band for one layer, and in dash blue is top of the valence band for the other layer. This is at 0 applied displacement field. And then if I apply a displacement field, what happens is the relative energy position of the 2 layer bands, they change as a function of displacement field. So in my cartoon image here, what happens as I apply a displacement field is I just shift one layer band relative to the other layer band. Now, the really nice thing about the consequence of that is that what I'm really accomplishing is I'm effectively changing the band width of this occupied band, or of this kind of isolated band, flat band. The other thing that happens as a consequence of that is we shift the position of the Van Hoff singularity. This is, again, just all calculated by kind of assuming single particle picture. Okay, so we can be slightly more precise than that. So here we're plotting the density of states as a function of filling of the band, and each color corresponds to a different displacement field value. And what we see is that indeed, the peak density of states, which coincides with the single particle Van Hoff singularity, shifts rather dramatically through the band as we vary the displacement field that we apply. So all of this tells us, when we first sort of did this work, it was a confusing question for us in terms of how to understand twisted bilayer graphene, because one of the questions that arose early was, where is the Van Hoff singularity in the band and how can we identify it and so on? And in this system, we actually know rather well from a single particle picture how the Van Hoff singularity position evolves with displacement field. And we think, based on the Hall resistance measurements that I identified a moment ago, that we can experimentally measure where the Van Hoff singularity is as a function of displacement field, and we can correlate these two results. So what I'm showing here basically is the experimental data point in black, tracking again the Van Hoff position as a function of displacement field. And here's the theory prediction from single particle band structure calculation, identifying where in filling the Van Hoff should be positioned as a function of displacement field. And the sort of argument here is that we see a fairly nice qualitative, if not exact quantitative, correspondence here. The qualitative argument, is that at zero displacement field, the Van Hoff begins slightly below half filling. And as we increase this displacement field, we can push the Van Hoff to fairly far above half filling. And that's exactly what we see in our data. Okay, so fairly good agreement, we think. Great, so that's sort of a detailed discussion of a measurement for a single twist angle device. We can repeat this measurement for all the different twist angle devices that we made, again, spanning from about 4 degrees to about 5.1 degrees. What limits this range is that at small angle, all of the sort of, interesting densities get sort of pushed into the disorder limit of the device and we can't resolve anything. And at high twist angle, things get pushed to too high of a density that we can't access, by gating. Okay, so nonetheless, within this angle range that we can access, we see a fairly remarkable, to my mind, evolution, like coherent evolution of the data. What we see is as we increase the twist angle, this half band insulator spans a well-defined displacement field for reasons that I just discussed. And the evolution of the boundaries of the displacement field seems to be evolving systematically with twist angle. So again, the question is, can we correspond that to single particle band structure? Because those calculations seem to do a fairly good job of explaining qualitatively the data we just described for the one device. And indeed, we can map out. So here I'm just sort of showing a plot of extracted gap. So this is gap sitting at basically a gap across this insulator. So as I vary d across this insulator, we measure the gap. We plot that here, and we plot that for the different twist angle devices. And we see that the gap spans different ranges. That's exactly consistent with what we see in this data. And we also just see here more quantitatively that the magnitude of the gap varies depending on which twist angle we're at. So 5.1 degrees, we see the strongest gap that we observe in any of our devices, and that diminishes as we go to smaller twist angle. So here we're just plotting representation of basically where the device is metallic, so where we leave this insulating regime as a function of displacement field versus angle. And we see that roughly there's a locus of points that defines this kind of pink region, defines where we might expect to see an insulator in our system as we vary d and vary twist angle. And then we went back to our collaborator friends, theory friends, and asked, basically, can we generate a 2D map of just the density of states at half band filling as a function of d and as a function of twist angle? And what do we find? And what we find is that there's, again, fairly good qualitative agreement between these two plots. So all that's really saying is it's, in my mind, affirming that we have a good handle on what's happening in these systems, that basically we get an insulating state that emerges at exactly half filling. That resistive peak only exists at half filling. So it's a state that really relies on the fact that we're at half filling or exactly one particle per Moiré unit cell. And we also have this kind of tunability in the system via displacement field. And really we can think about that tunability doing kind of two things really. One is that the displacement field varies the effective width of the slow energy band. And the other is that the displacement field allows us to tune simultaneously where precisely the Van Hoff singularity is in this band. Okay, so that the strength of the insulator at half filling seems to coincide well with the position of the Van Hoff singularity. We interpret generally as telling us that these systems, at least in this angle range that we're studying, are in maybe a regime of like moderate interaction strength. Excuse me. So we have this scenario where we have something that's a Hubbard-like model. We have a triangular Moiré pattern. And we see that when we reach half filling, a correlated insulator emerges, but that insulator is tunable with density of states, essentially, which is what we're tuning by tuning the Van Hoff singularity, which again suggests we're in some region of like moderate interaction strength. We're not very strongly interacting, and we're also not very weakly interacting. That's at least our interpretation. Okay, so one of the questions immediately is like, what's the what's the magnetic order of this ground state at half filling? And the answer I'm going to give is that for this system, at least so far, we don't have a good understanding of that. I'm showing here just some magnetic field dependent measurements of the half band insulator gap. So how that gap evolves as a function of B and as a function of displacement field. And what we see is that generally beyond some threshold magnetic field value, the gap indeed decreases. So, the average, the sort of, initial interpretation of that response would be that we have something like an antiferromagnetic insulator that describes this insulating state. But it's not so straightforward. There seems to be a sort of a curious regime of B field over which the gap initially begins as sort of insensitive to magnetic field. This is field out of plane, I think in this case. Or for some displacement field values, actually it's non-monotonic even. So we see that for some range of displacement field, you can see that well on this plot. First the gap increases and then it decreases again. It's sort of reflected roughly here. Okay, so again, exactly what this is telling us, we don't exactly know. And we're trying to study this further, sort of get a handle on whether there is a variation in the magnetic order of the ground state that depends on the displacement field value or the twist angle, etc. Okay, so the final sort of initial finding that we had was that was the question of whether there's superconductivity in the system. So this remains for us kind of an open question. Initially, at least on one of the devices that we measured, we were able to observe some pockets of response around the insulators. So we doped either positive or negatively relative to the insulator. There appears to be the onset of some low resistance or zero resistance state. I'm a little bit hesitant to sort of definitively call this a superconductor for reasons that were alluded to a little bit earlier today. One is that similar response that we also measured in twisted bilayer graphene. Eventually, the conclusion was that that probably is not necessarily evidence of a superconductivity, but may rather be evidence of some temperature-driven reconstruction of the Fermi surface, for example. It's not very clear. One of the challenges of this particular system, as I keep emphasizing, is that contact resistances are rather terrible. So we're trying to make an assessment about whether we have superconductivity in a system where generally we might find that our two-terminal resistance is of order, it could be as high as 100 kilo ohms in some devices. So it's a little bit fraught to make very specific claims. What we did notice is that this particular device, which is the only device that we measured something that we might suggest indicates possibly superconductivity, is the device in which we, so here's some other kind of metrics we measure, is the same device in which we measure the strongest insulating gap. So that might be suggestive that, if there is superconductivity at all, it might be manifesting in systems where we have the kind of strongest electron correlations in the band. If we take the size of the insulating gap as reflective of being sort of, somehow indicating the strength of correlations in the band. Okay, So one last thing, final thing we noted in these devices was that if we looked more carefully in the low density regime, so here, again, this is half filling, this is the half filling peak, plotting temperature versus density. If we go to very low density, but we go to higher temperature where things are not totally frozen out, and we can resolve some transport features, then in that case, we see multiple oscillations in our data. And those oscillations, it appears, we can coincide with fairly well-defined fractional fillings. We didn't study this a lot. It wasn't exactly clear to us how robust this assignment is. We can, for example, identify that these might coincide with some charge density wave states with commensurabilities that are either something like bubble or something like stripe phases coinciding with the Moiré potential wavelength itself. There were several other reports of studies of these in the heterobyte layers. So this is work by Phai's group at Cornell, Jian Phai's group at Cornell, and also Feng Wang's group at Berkeley. In the heterobyte layers, they found that indeed there's sort of ubiquitous evidence of there being charge density wave states in these systems. So we think that's likely what's going on here, but we haven't yet gone back and studied these in detail. Okay, so in the maybe next 10 minutes or so, what I'm going to discuss is some kind of more detailed studies we made of these systems. So just a summary of, the big picture of what I discussed so far, even if the details are maybe up for sort of, debate. What we think we have access to in this system is basically a tunable 2D Hubbard model. The idea is that we have a 2D triangular Hubbard model specifically. We have a triangular superlattice potential arising from the Moiré potential that exists in these systems as a function of twist angle. The length scale of this triangular potential is just directly determined by the twist angle itself. But at a fixed twist angle, we can further modify the bandwidth, for example, by using transverse displacement fields. So we have these gates top and bottom. And for a fixed twist angle, we can, as I just argued, tune this bandwidth by just applying a transverse field. But at the same time, we can also tune the filling. So basically by asymmetrically coupling to these gates, we can tune the bandwidth. By symmetrically coupling these gates, we can tune the filling, and we can independently control those two parameters. So this is actually quite interesting. So here I'm just showing sort of cutting through this diagram in one or two ways. Because generically, one expects that the Hubbard model has this kind of cartoon sort of phase space that you can access, where at exactly half filling, you have like a Mott gap that emerges. And what's interesting is that you imagine that you can tune through this Mott gap either by varying the filling, so either doping into and out of the Mott gap or doping into and out of exactly half filling, or through some modification of the bandwidth itself. Or another way to say that is through some modification of the strength of how strongly correlated the system is. Now, what's interesting about this experimentally is that generally this kind of tunability, although you might access this phase diagram in more conventional systems, this kind of tunability is not necessarily accessible in a dynamic way in a single material. You might have to, for example, like vary the doping through substitutional doping, et cetera, which might be varying other kind of constants of the system. And you might have to sort of vary the precise nature of the band structure through some other complicated means. But here, just through like field effect gating, we can get access to both of these axes. So we went back and decided to investigate this a little bit more in detail and just see if we can map more carefully what happens as a function of tuning in and out of this insulating state using the field effect control that we now have access to. And we're going to tune both in the filling direction and in the what we call sort of band tuning directions and see what happens. Okay, so just to sort of orient yourself here, here's sort of the generic sort of cartoon diagram. If you like, what we're able to do is sort of tune completely through this space, or maybe a simple way to understand this is if you just flip this over, here's the kind of like right at this point is the point that sort of maybe corresponds to this point in this diagram. So as I increase the displacement field, I increase the bandwidth in this system. So I tune from a strongly correlated system maybe to a weakly correlated system. Okay. The other thing to just sort of keep in mind is that this window, we can access fully this window through, again, symmetric and anti-symmetric bias gate voltages. But the sort of central position of this window, the range, the extent we can access is really very specifically determined by the twist angle in the device. Okay. Good. So first, let's look at what happens as a function of density tuning. So here I'm plotting in a device, I think this is the 4.2 degree twist device, just a focused sort of temperature density, filling dependence here. So here, filling 1 corresponds to half filling, or this has become, I think, a better nomenclature. Filling 1 corresponds to exactly 1 hole per Moiré unit cell. And at this point, I have this, this Mott gap that we observe. And what I want to do now is look at what happens is if I'm on the positive doping side of this Mott gap. And here we're just sort of plotting R versus T line cuts. What we see is that indeed, as I move from the insulator to higher doping, we transition from an insulating-like state to a purely metallic state. And if I dope in the negative sense, so fewer holes, if I underdope relative to this dome, same thing, we transition from a insulating state to a metallic-like state. Now, what we can sort of look at in detail is how precisely the resistivity varies as a function of temperature in each of these regimes. And what you might be sort of, willing to see, and we'll discuss in a little bit more detail, is that there's a line here, we label this, we color code this black, where we see something that looks like a linear T dependence over a finite range of temperature. Okay, so the red curve here very specifically looks like it's kind of parabolic. The green curve is very clearly insulating. And at some curve between these 2 points here, we have nominally a linear rho versus T dependence from the lowest temperature we can measure in this device up to about 10 Kelvin. Okay, so if we just take the temperature derivative of all these curves, basically this plot, and we replot that, then what we can identify and label is basically the entire phase diagram as we transition from the insulator through this kind of T-linear regime as a function of temperature and filling now, and then to something that looks more like a Fermi liquid regime, T-squared dependence. Okay, so let's look at this in slightly more detail. So here again is just, I'm showing over a fairly narrow range of temperature and filling. So here, if we go to a much broader range of filling, so spanning now, a broader range of density, and a much broader range of temperature, then what we can look at is how this this evolves really over that over those boundaries. So again, the critical point here I'm just trying to emphasize is that there is a region of doping far away from the half band insulator where we very clearly see something that looks like a parabolic dependence. There's a region where we see something that looks kind of very more convincingly like a T-linear dependence. And then at low doping, there's a region where we recover this T-squared dependence. And also at very high temperature, we observe that we see a saturation in the rho versus T, very high temperature regime here. So this one I'm not going to talk about too much. We don't exactly understand where this is coming from. We really don't understand it all. And I'm not going to sort of describe it more, but if people have thoughts about that or wish to discuss it more, I'm happy to sort of discuss the data a bit more. Okay, so here's just a summary kind of like cartoon diagram of what we see. This gray curve here is identifying where we have the half band insulator. This gray region here is identifying where we have the full band filling, where we see something that's sort of more insulating-like. And over this temperature range and density range, what we see is that around the half band insulator, we seem to see a fairly wide range of doping where we see something that really is T-linear behavior. So in correlated systems like cuprates and heavy fermion systems, et cetera, this is what might be identified as a strange metal. So in this system, I want to be a little bit careful. There's can be a lot of heated debate when you sort of bring up the notion of a strange metal. Historically, a strange metal is defined as having a linear T dependence from the lowest measurable temperature range, really to the highest measurable temperature range that you could access. Here, our T-linear regime cuts off at some high temperature value where we see the saturation dependence. And partly why that would be not unexpected in the system is that we have quite a finite bandwidth in energy, beyond which if we heat the system too much, we start to access the higher temperature band, higher energy band, sorry. Okay, so if you sort of allow me for the moment, we're just gonna sort of discuss the low T behavior in terms of whether it's T-squared or T-linear. The other thing we can do is we can plot basically the coefficient of that behavior. So we call A naught here is the coefficient of the t squared behavior. AL is the coefficient of the t linear behavior. And what we see is that actually both of these peak at around a similar point. And we identify that point as evidence of the quantum critical point in the end. So we say that, this point identifies, if we imagine we project all the way to low temperature, we're assuming that this point identifies the precise crossover where we transition from the insulating state and this kind of t-linear behavior to the t-squared behavior, the kind of more conventional behavior. The other thing we note, I don't think I have it sort of well articulated in this plot, is that where these two coefficients peak, where they diverge, and if we take that as the quantum critical point, coincides with the density at which we see the kind of greatest temperature range over which we actually see t-linear behavior persisting to the lowest temperature range that we have access to. Okay, so all this we believe is allowing us to identify really a quantum critical point in the system. We observe that we have two quantum critical points, one on the overdoped side and one on the underdoped side. And we also note that away from that, we have really this kind of beautiful t-squared dependence, which identifies that there's a strong filling dependence in this system, which is a bit unique compared to similar discussions. I didn't recap it here that we had about sort of t-linear behavior that may or may not exist in the graphene just bilayer systems. Okay, so one of the sort of open questions is this high temperature saturation behavior, which again, I'm not going to discuss too much. So that's what happens if we bandwidth tune. If we tune by filling, so we dope in and out of the half band filling regime. What happens if we bandwidth tune? So here I'm sitting at fixed half filling and we apply a displacement field. So here now this curve is a large displacement field and small displacement field. And what we see is that here we can tune from an insulating state to a metallic state by bandwidth tuning alone. So again, sitting at fixed filling. And again, there's a regime, if we like, of like a critical displacement field where we see what appears to be very well described linear T behavior down to the lowest temperature of the fridge that we measured this in 2 Kelvin, about 1.6 Kelvin, sorry, which we identified therefore as the quantum critical point in the system. So this tells us that we can achieve the quantum critical point. We can reach it both by band tuning and by density tuning. I'm running a bit out of time, so I think I'll sort of skim past this. Here we're sort of correlating parameters that we measure through bandwidth and density tuning, but I'll sort of move past that. One of the kind of peculiarities that we identified is that if we look at R versus T behavior at half filling, then you can see here, for example, that as I indicated in the previous plot, there's a well-defined linear dependence at temperatures above which we have the insulating state. So the insulator at low enough temperature, and that gives way to this kind of T-linear behavior. And what we observe is that if we bandwidth tune in and out of the Mott gap effectively, so if we have a displacement field value where there's a well-defined gap or there's not a well-defined gap, then we can identify this parameter, which we call the residual resistivity, which is we just project this linear T behavior to 0 temperature and ask what's the residual resistivity value there. And if we plot that residual resistivity as a function of displacement field, we see that it's roughly a constant value, and then it abruptly transitions to a 0 value. And that transition point is the same transition point where we induce the existence or non-existence of the Mott gap. So this regime here is basically defining where there is the Mott gap. This regime is defining where there is not the Mott gap. So there's really a kind of abrupt step in this residual resistivity. So what this precisely means, we're not exactly sure. There is some indications in some theory work that this abrupt change in the residual resistivity is something you might expect. And you might be able to correlate that with the existence of some superfluid transition in the system, not superfluid, sorry, a spin liquid transition in the system. So I'm not asserting that, I'm just asserting that in the data we see this kind of abrupt change, and that may or may not indicate something interesting. Okay, so the last thing I want to just sort of touch on is that we measured the magneto resistance around this metal insulator transition in some more detail. And this shows kind of a really exotic behavior. Here in the top left, sorry, I'm showing longitudinal resistance right near the quantum critical point on the overdope side. Here on the left is longitudinal, and on the right is the Hall resistance. What we see is that the longitudinal is dramatically non-monotonic. It shows a strong positive magneto resistance, and then that sort of shows a peak, and then it shows something kind of a little bit recovers the positive magneto resistance again. The Hall resistance is a little bit even more strange. It shows this kind of like really massive increase in the Hall resistance as a function of B as we tune slightly away from 0B. If I go to the underdoped side, then the curious thing is that the response is quite different. So here we see now initially very close to the insulator, actually a negative magneto resistance, which then beyond some threshold B transitions to a positive. And here we see that the Hall resistance is kind of much more well-behaved. So this is kind of early data. This is more recent, and we're trying to sort of figure out what this exactly means. One generous interpretation of this Hall data might be that this indicates something like an anomalous Hall response. In that interpretation, it might be indicating that we have some ferromagnetic ordering if we're on the positive dope side, and that we transition to a different behavior on the underdoped might indicate that whereas overdoped is ferromagnetic, underdoped may not be ferromagnetic. So that again is almost speculation at this point. I wouldn't say that really our data is really evidence of that. It's sort of an interpretation possibly of our data. One of the things we've done is to discuss this with our friends at mostly the Flatiron. And they came out with a paper recently in which it's on the archive, in which they tried to calculate for a system like ours, what might you expect the ground state ordering to be around this metal insulator transition? And how does that evolve as a function of interaction parameters here on the vertical scale and doping on the horizontal scale? And all I want to point out is that forgoing the details, they find that it's plausible that you might expect that there is different magnetic ordering states on the overdoped side versus the underdoped side. And the precise nature of those states would be dependent on the precise interaction strengths that you have in the system. Okay. I know we were running a little bit late, so I think I maybe have like 5 more minutes. So let me just not go too much into detail. Let me just say, because I think the next talk also is going to be more detail of this. Let me just finally say that in addition to homo bilayers, we can study hetero bilayers. And in the most broad view, one of the sort of like interesting features of the hetero bilayer is that we simplify the system even further. So here's a rough cartoon picture of the band alignment for a hetero bilayer. Now we have that, in this case for WSE2, WS2, the band alignment is such that one of the layers is pushed to a much lower energy than the other. So we still get a creation of a flat band in the system because there's a Moiré potential that develops, and that Moiré potential induces basically a like a flat band at the top of the valence band of one of the layers. But because the other layer has an energy offset, there's no hybridization between the layers. So we really have like a very pure system now. We have a single kind of valley state of one of these layers, basically. Okay. So there are many combinations that you can sort of pursue. Basically any transition metal dichalcogenide that exists, you can put in connection with another one and twist them around. And there's a natural lattice mismatch and then a twist-induced mismatch. And that gives rise to a really large phase space of the kinds of like band widths, band energies that you can deal with in these systems. Okay, so here I'm just looking at one. This is, we were studying, I think it's WSC2, MOSC2. And all I want to highlight here is very briefly, this is work by the Passipathy group. STM work showed that indeed, based on the stacking orientation, you can get very different symmetries of the Moiré lattice that exist in these systems. And also you can get really dramatic effects in terms of the effective magnitude of the Moiré potential that exists in these hetero bilayers. So here in this particular system, they identified evidence that the Moiré potential could be as large as several hundred MeV. That's much larger than we anticipated we could get in, for example, the case of twisted bilayer graphene or graphene coupled to BN, et cetera. One of the consequences of that we may have seen already. So here we're studying transport in a twisted WSE2, MOSC2 system. This particular device is twisted to 1.2 degrees with a Moiré wavelength of about 15 degrees. And all I want to highlight here is that, I'll skim the details here a little bit, is that if we cool the system down, then what I'm plotting here is capacitance measurement. Yellow basically means it's insulating, blue means it's not insulating. As we cool the system down, what we see is that the half band insulator emerges quite strongly. But if we are doped, if we underdope, so if we go to lower doping, below some kind of threshold temperature, actually the whole system appears to become insulating, becomes incompressible by capacitive spectroscopy. And if we overdope, it again is the case that the whole system, as long as we're less than filling fraction 2, is insulating. And that crossover appears to happen at a fairly well-defined transition temperature. But it happens at a different transition temperature for filling between 1 and 2 versus filling less than 1. So our interpretation of this data is that, in fact, the whole system basically is localized. And it might be the case that it's localized because the Moiré potential is potentially so strong in the system. So we imagine that we have essentially our electrons are just localizing on the Moiré sites for all fillings, basically, in the flat band. And then as soon as we exit the flat band, that's no longer the case. We now have sort of, a compressible system again. Okay, I'm going to skim some of these details. The other thing I just want to say is that this device is at a Moiré wavelength of 15 nanometers. We studied a similar device where we twisted to the case where the Moiré wavelength is 5 nanometers. So a fairly different regime in the business of Moiré superlattice potentials. And now what we see is that this behavior better resembles actually what I've been talking about for most of this talk. This is a heterobilayer WSC2 and WSC2. The response looks very much like homobilayer WSC2, WSC2. We've got basically a feature that emerges at half band filling. And in particular, the last thing I just talked about, if we look at magneto resistance in this system, we see that actually the magneto resistance shows a similar evolution that we observed for our homobilayer systems. So at slightly overdoped from the half band insulator, we have a positive magneto resistance in XX. As we go to underdoping, that transitions to a negative magneto resistance. And if we go further underdoped, so near the band edge, we recover again a positive magneto resistance. So we again are tempted to interpret this as indicating some variation in the ground state order if we compare over versus underdoped. And in particular, what's interesting to us about this is that it seems to suggest it really is a universal behavior in these systems, independent of what precisely makes up the material combination. These flat bands seem to be sort of like well-defined flat bands that are whose characters might be well captured by simple theory. Okay, let me finish there. So that's definitely the end of my time. I think it went a little bit long. I apologize. Let me thank the many people that have been involved over the years that these studies have involved now. And I'm happy to take any questions that anybody has.
All right. Thank you very much for the very wonderful talk. Since, again, we are already behind the schedule, maybe just one short question.
I'll ask a question. Cory, how low in temperature do you go? Can you produce the temperature dependent resistivity data you showed, showing from which you conclude where the metal insert transition is?
Yeah, I'll give you the short answer is we haven't actually cooled below about 1 Kelvin yet.
Yeah, so I have a very specific question and a prediction. Just keep on going back. The main figure for your, these are all derived. Yeah, this one.
Yeah.
So here I can think of this nu as various effective carrier densities. So how much is the carrier density changing in per centimeter square?
It's a full range. So around this doping, it's probably, I don't know, 10 to the 10 or 10 to the 11, something like that.
Yeah, let's look at the figures on the right, where you actually plot your resistivity as a function of temperature.
Yeah, it's going to be probably order 10 to the 11, I'm guessing.
10 to the 11, right? And and how low do you go in temperature? It looks like you go down only to 2 Kelvin. Is that correct?
Yeah, 1.6. That's right.
Okay,
Yeah.
so let me predict that if you go down further in temperature, you'll find there is no metal here. Every single curve turns up. There's a specific prediction, and I'm 100% confident in it. There is no metal insert transition here. Metal insert transition is a zero temperature property. And all of these will carve, is what I predict. Okay.
All of these will what, did you say?
All of these, every single line that you have will carve just as your lines. All of them will carve. You just didn't go to low enough in temperature, meaning there is no zero temperature metal insert transition here.
So that's the question. So this is always the question of, I guess, defining a quantum critical point.
No, but I mean, you are only at 2 Kelvin. I mean, nobody would claim a transition at 2 Kelvin. I'm not saying that you have to go to 0 Kelvin. I'm saying that you should at least go to 50, 60 millikelvin. Yeah. And then at least the lines that you are showing here will all carve. I cannot say that, something even at lower temperature will not carve. You understand what I'm saying, okay? I mean, this is not enough to conclude anything, is what I'm saying.
I totally agree with you. So I think, one of the, just, basic definitions that you just said of a quantum critical point is that it's a zero T phenomenon. So at a minimum, our expectation, I don't know if I painted the picture clearly enough, but our expectation is that, I guess what I'm asking is, so we think the quantum critical point is right here.
Yeah.
Many evidence of that. And the question is like, does this boundary and this boundary, do they close before you get to zero temperature? That's basically what you're asking, I think. Right?
That's correct. And
Yeah.
the reason is the problem that you have some disorder also.
Yes,
I'm not saying there's no quantum critical point, but you have some disorder also. So what would happen basically at low density, even if the system is kind of quasi-metallic, you'll have a percolation transition, completely classical transition, okay, as what happens in silicon MOSFET and so on. And so quantum critical point will be subsumed in this percolation transition. And then, it's a very interesting question. I cannot tell you exactly, I know what's going on, but I think quantum critical point, if there is any, is inaccessible. We can talk about it off the line. I have been thinking a lot about these figures, and I would urge if it's possible to go to lower temperature, down to 100 millikelvin at least.
Yeah, so I think that's, for what it's worth, we're working on that now. So we've improved contact resistances. We have accessible Dilfridge now. So that'll be coming soon, hopefully.
Yeah. I would not have asked if I didn't think you could do that. Yes.
Great.
Yeah. Thank you.
Thanks.
All right. Let us thank Cory again for the wonderful talk.
Okay. Thanks.